All right, hi. Let's do 100%. American Railway Signal Principal Practices, Chapter 8, Transformers. Public Signal Section, Association American Railroad, 59 East Van Buren Street, Chicago 5th, Illinois, Chapter 8, Transformers. Published in the Association American Railroad Signal Section, 59 East Van Buren Street, Chicago 5, Illinois. Copyright 1953 by Association American Railroad Signal Section. All right. The Signal Section Association of American Railroad defines the transformer as a stationary inductive device generally used for the changing of the ratio between voltage and current in an alternating current circuit for the insulation of one part of the circuit from another. A transformer does not generate power but merely changes the power from one voltage to another the same frequency as the energized circuit. Alternating current for a signal is generally transmitted from a power station, the signal field with the voltage main. High voltage on mains are changed from lower voltage to mean of transformer. One method of lower voltage to be successive steps, that is, to use the transformer to lower the voltage of 115 volts or a single motors, etc., then further reduce the voltage using another transformer feed from the track circuit to low voltage signal amps. Another method is to use one transformer to the lower voltage of all purposes. In the theory, in general construction, all transformers where line and track are the same. The chapter will deal principally with the transformer specifically designed for the railroad signal service. Elements of the transformer simplest form of the consists of two separate distinct coils insulated with wire around them and has illuminated iron core as shown in figure 1. From the power supply to the load, iron core wrapped around primary and secondary. One coil is attached to the outside of the energy, and this primary coil, the other coil, is transmitted with the energy from the transformer. Secondary coil transformer may have more than one secondary coil, or have a secondary coil tapped at a different point to produce a different voltage. When a transformer transmits higher voltage, then it receives it, known as the setup transformer. The setup transformers are used as a power station to raise voltage of the generator to the transmission voltage of a transformer that transmits a lower voltage, then receives a known as a step-down transformer. Step-down transformer are used along the transmission line and signal locations interlocking tower to transform the high voltage of the transmission lines to the lower voltage for the signal purposes. When the secondary circuit is open, the alternating current from the transmission line flows from the primary coil. It causes the alternating magnetic flux to flow into the core, with the magnetic flux rapidly rising and falling and changing direction with the frequency links both in primary and secondary coil, inducing the voltage in each. Voltage induced for the primary coil opposes the flow of the current and nearly equal to the voltage applied with the primary terminals. The voltage of secondary coil is proportional to the ratio of the number of turns of the wire in secondary coil to the number of turns in the primary coil. The choking effect produced with a highly inductive primary coil allows only the small current to flow continuously through it, and all small alternating current, known as the exciting current, produces a very magnetic flux in the core, which in turn induces the voltage. Primary and secondary coil describe the inducing voltage that primarily used to call the counter electromotive force. When the secondary circuit is closed, the current flows through it, and then the secondary opposes the primary current with the magnetizing action. Core opens and neutralizes to a certain extent with the primary flux, reducing the choking effect with the counter electric motive force in the primary coil. When this happens, more current rushes into the primary coil from the transmission line, balanced with the demagnetizes action. Secondary current, the transformer is made and automatic maintains a core flux practically contained regardless of the load of the secondary. The variation of the load through the primary varies directly with the load of on the secondary. Alright, losses. All energy drawn from the transmission line of the transformer does not transform. The smallest part used for the precision process analogous to the energy loss of the machine through the friction in modern well-designed transformers. The losses are so small that in proportion to the normal load on the transformer that the practical purpose that they are rarely considered, but it is well known to them. Energy is lost when required to maintain a flow of flux in the core, sustaining the voltage in the coil. This loss is particularly constant with or without load. The alternating magnet flux causes the loss of the iron core, called the iron loss, is known as the hysteresis or an eddy current loss. Hysteresis loss is an energy spent in overcoming the friction between the molecules of an iron that may be moved backward or forward with the change of the direction of flux. This is theoretically, as some of the belief is not natural, the resistance of the metal of the flow of flux, that molecules of iron do not move backward and forward. The eddy current loss is an energy spent in the heating action of the current inducing the iron core by the varying of the flux. Voltages are induced with the core, and by alternating flux, these voltages precede eddy currents. Iron losses are particularly constant with or without load and are made manifest by heating. Due to the load of the transformer, the total copper loss in the transformer is I squared by R of the primary per plus, or I squared prime by R on the secondary. Magnetic leakage. Reference to Figure 1, which will explain the effect of magnetic leakage. Dotted line M represents the flux which passes through both secondary and primary and secondary coils. The portion of L1, the total primary flux which passes through the leakage that does not link into the second coil. When the current flows in the secondary, leakage flows from L2 that is developed, which does not link the primary coil. Usually tends to oppose the main flux M, depending on the power or the factor of the load circuit. The voltage induced in these leakage fluxes respectively cause the reactive drops in both windings and analogs, and resistant drops caused by magnetic resistance of the coils. This result is the same resistant reactants were added in the series of the winding of the ideal transformer having no leakage. The reactants are practically consult in value of the voltage drop caused by them, therefore vary directly as the current in respective windings. Coil resistant magnetic leakage are shown graphically in Figure 2. Figure 2 shows the coil resistance magnetic leakage form primary and secondary coil with resistance 1 and 2, and also the I guess the you have your resistance and your I think it's capacitation line or current. E1 equals the transmissional line voltage. E1 minor E1 primary total voltage after drop is caused by automatic resistance lower R1 primary coil reactance X1 caused by the magnetic leak. E1 is greater than lower E1. E2 is the net terminal voltage of the secondary. Lower E2 is the induced voltage of the secondary before the drop is caused by the automatic resistance at R2, the secondary coil, with the reactance of X2 caused by the magnetic leak. Efficiency equation with the transformer is also as follows: power output of the secondary, power output of the secondary divided by power of the output of the secondary plus transformer loss. When iron loss is small and transformers have high efficiency on light loads, when the iron loss is equal to the copper loss, the transformer have efficient full load or overload. Input of watts and primary voltage relationship of the primary and secondary coil. The fundamental equation used to design the transformer is as follows: the inducing voltage secondary coil or primary coil is 4.44 F frequencies in cycle times the maximum flux of sine wave times the number of turns in respective coil divided by 10 to the 8th. The voltage of the secondary primary coil are proportional to these respective turns, but both of the same frequency cut in the same flux. Due to the automatic action, transformers will cause the core to remain constant regardless of the load. Primary and secondary induced the voltage means are practically constant. The neglecting voltage drop due to coil resistance and magnetic leakage is voltage of primary over voltage of secondary equals turns of primary over turns of secondary. Voltage primary multiplied by the turn of the secondary is equal to the voltage of the secondary multiplied by the turns of the primary. The ratio of the transformer is the ratio of the number of the turns in the high voltage, and so that the low voltage winding approximately the same ratio of the turn voltage is explained in the foregoing. The transformer is 23,000 volts primary, 115 volts secondary, for the result of a ratio of approximately 20 to 1. Ampere turns defined in signal section AAR for the measure of the magnetism power, motive force developing current electricity conducting coil is equal to the product of the number of the turns in the coil current with the amperes designed by the NI. The magnetic force can be increasing the number of the turns of the current. Equivalent can be produced by the increasing the number of the turns and decreasing the amount of current, the vice versa. The magnetic action of secondary coil is proportional to the current of the secondary coil multiplied by the number of turns in the coil, designated by N2 times I2, N scripted 2, I scripted 2. The magnetic action current in primary secondary coils is Ni is equal to N2 over I2, 1 over something is equal to N2. I can't tell you what that is. A transformer of 60,000 turns of the primary coil, 300 turns of the secondary coil, and a power supply of 2300 volts. We see that the equation for the secondary voltage is equal to 2300 volts times 300 turns in the secondary coil is divided by 600 turns of the primary coil is equal to 115 volts. The secondary transmits to 10 amperes. We see the equation 5 current in the primary is equal to 300 times 10 over 6,000, which is 1/2 ampere. Effective power factor. The power factor is defined with the ratio active power, the apparent power of the voltage, ampere, the power of the factors of the alternating current, unity, watts, current, voltage. The power factor of the alternating current is less than unity, watts, current, voltage. Power factor of the transformer transmitting at 10 amperes for the secondary to do certain when the load with the unity power factor would be returned 20 amperes, the same amount of the work is loaded with the power of the factors and a half. As often happens in a single work, for this reason, capacity of the transformer is stated as in kilovolts times amp, or volts, kilovolts, amps, or 1,000 volts or amperes. Note that kilowatts is 1,000 watts. Kilo is an abbreviation for kilo, the Greek meaning 1,000. The capacity of the transformer is number of the kilovolts for amps. By kilovolts amperes transformer designed to carry the when zero is angle of leg of the secondary current, when the cosine of the power factor of the secondary current is where the angle of 0 is 60 degrees cosine 0 and the power factor is 1/2. When the angle is 0 and 30 degrees cosine of 0 and the power factor is 0.87. And when the angle is 0.15 degrees cosine is 0, power factor is 0.97. The calculation of core loss. Core losses. Formulas was developed by the late Dr. Steinmetz to determine the high Steinmetz. He was a midget. I saw a thing on WED about it. Determine the hysteria and eddy current loss of the force of the given with the flux density shown by the hysteria. The loss varied with the frequency. The eddy current loss is varied with the square of the frequency. The calculation of the core loss of the formula would be quite complicated. It is now general practice to determine the total core loss from the curves which have been prepared for the steel manufacturer. The curves of one of which was shown in Figure 3 gives the watts, current loss, volts, or amperes, exciting current per pound of iron with the given the flux density, the frequency, and thickness of the particular grade of the transformer steel, and use the total watts obtained from such something divided by the primary rated volts and given. Alright, Figure 3 shows the core loss of curves, the current loss of the voltage, amperes, the grade, the gauge, the frequency, the note, and curves of 1 and grade 2. This is core loss curves by the watts and volts, amperes, pound by kilo lines per square inch. Regulations. When secondary is transmitting power, the circuit is open with the load removed with the voltage. The secondary will rise. The amount of the rise voltage expressed in percent of the secondary full load of the terminal voltage is called the regulation, and impressed with the primary voltage being the constant. For example, the secondary voltage of the full non-inductive in load with the 110 volts with 114 volts when loaded is removed. Regulation is equal to 114 volts minus 110 volts divided by 110 volts, which is 3.64%. Reproduce the courtesy permission of the Cargill Illinois Steel. Then addition to the receiver, the drop of the magnetic leakage, the often necessary to calculate the regulation to determine the valve of the resistant reactance drop. The quantities vary with the load and the power factor. The formula recommended to the United States Bureau of the Standards unity power factor non-inducive load is regulation is equal to I 100 times IR times 100 times IR over E is equal to the percentage. A 60% power factor regulation of 0.6 IR or 0.8 PA is equal to divided by E, where E is rated with the primary voltage rated secondary voltage multiplied by the turn ratio. P is the reactance voltage dropped at the full load, and I is the full load primary current, not including the exciting current. The equivalent of resistance R is combined with the primary and secondary coulomb found with the multiplying secondary resistance by the square of the ratio of the primary and secondary turns into adding the primary resistance. Impedance of the voltage E, lower E, is found with the short-circuiting secondary measuring voltage required to send the full load of the current through the primary. Impedance of the voltage lower E is divided equal to the square root of P squared times I squared times B squared plus I squared plus R squared, transposing that P is equal to the square root of lower e squared minus the I squared r squared equation. And this design transformer regulation is approved by the use of the wire largest possible cross-section area of the copper that is given to the minimum resistance of the coil by interlacing the primary and secondary coil to decrease the magnetic leakage. The interlaced winding of the primary and secondary coils are wound in several sections connected to a series of sections alternated by in the position of the core. The later is known as is not common to transfer, but the most application signal performance rating. Table 1 illustrates the performance of high-grade commercial transformers regarding loss efficiency regulating various voltages and something else. Alright, figure, this shows it doesn't say, but it's wire, full load, half load, quarter load, 100% PF, 80% PF, 60% PF, kilovolts for amperes, and this is transformer something rating, I guess, ratio over the secondary and primary, I don't know. It doesn't say. We'll increase the size of this again. Transformers are rated according to voltage, ampere to kilovolt, ampere to delivery, continuous non-inductive load with overheating to secure the uniform in rating. The ASA recommends the transformer class for A insulation operating continuously full loaded through the temperature rising windings should not exceed ambient temperatures by more than 90 degrees Fahrenheit. The temperature are specified in the base of life expectancy. Insulation, assuming the definition surface of the conditions, the surface conditions is considered with the cooling quality of the air and are the temperature of the cooling air. Ambient temperature does not exceed 104 degrees Fahrenheit. The average temperature of the cooling air for the 24-hour period does not exceed 86 degrees Fahrenheit. Second, the altitude does not exceed 3,300 feet. Transformers were applied to the higher ambient temperatures or higher altitudes with specified load and continuous maximum capacity should have the special consideration as effect of these variations. The manufacturer is usually consulted with respect to what the reduction rating should be applied, if any. The average temperature of the cooling air can be determined by the averaging of 24 consecutive hour readings of the outdoor air as cooling with a medium and the average of maximum and minimum daily temperatures may be used in selection, but the transformer of the new work replacement is desired to be specify the capacities and voltage preferred in commercial ratings. Figure 4 shows the characteristic curve of 1 1/2 kilovolt transformer. Alright, figure 4 shows the curve of 1.5 kilovolt, or characteristical curve from 2300 volts to minus 230 volts of 115 volt, 60 cycle 1.5 kilovolt ampere oil immersed self-cooled signaling transformer. You have your percent efficiency, your percent rated load of the power factor load, your percent regulation and percent losses with the copper loss at the varying loads, full loaded resolution varying power factor, percentage of the loss of the varying loads, a percent of the total loss of the varying loads, and efficiency of percentage of varying loads. Different frequencies, the lower frequency, the larger must be the transformer in order to deliver a given output with the overheating of the frequency, generally with the signal work of the 60 to 100 cycles. In some instances, frequency of 25 cycles is used. The transformer is designed with a certain work of the 25 cycles to perform the same work of the 60 cycle transmission line with less heat than one of the 25 cycle transmission line. The same same applies with the 60 cycle transformer used with the 100 cycle transmission line. A 25 cycle transformer connected with the 60 cycle transmission line would have its coils and by magnetic flux more than twice the rate would be cut in 25 cycle transmission, therefore requiring the lines that is forced to perform the function sustaining the voltage and coils. Smaller iron core accommodated them, and therefore by evident transformer design the certain frequency should not be used in lines. However, the lowering frequency and excessive current will flow through the primary core, causing overheating, thus causing overheating. Vector diagrams. Vector diagrams are ideal transformers working on no load are shown in Figure 5. Ideal transformers are considered as having no loss resistance so small that it is be negligible. Flux generated with the iron core varies periodically, accompanying the phase of the magnetism core with producing it. The voltage induced by the primary and secondary coil is changing from the flux of 90 electrical degrees ahead of the time phase leading with respect flux produced with the magnetizing core, meaning because the inducing voltage maximum within the flux is changing most rapidly with the 0 point. By primary magnetism of the current M, the secondary voltage has been shown with the opposite phase of the primary voltage instead of the phase of conveniency, making the diagrams, keeping it with the method that has been used with the past by many authors in texts like electrical theory. E1 voltage applied with the primary terminals and same as the lower E1 ideal transformer. Similarly, the voltage secondary terminals in E2 the same as the lower E2 since there is no current flowing with the secondary. The actual transformer vector diagram no load condition is shown in diagram B with the figure 5. The eddy currents for the iron core have an effect with a similar or small amount of secondary load current, thus causing the primary to draw the additional current with the balance and demagnetizing effect of the currents because of the eddy current and the high hysteresis losses of the iron core component with the MIO subscripted 0 phase is applied with the voltage is added to the magnetism core of current OM, resulting in the torrent coil of O to the I subscripted 0. There's no load, which is also called the existing current with the voltage drop. Due to the small current, primary resistance leakage resistance is usually negligible. Alright, here's the vector diagrams of the transformer working on no load. With the you see the E1 and E1 and E2 and E2 on the 0 to MA and also E2 and E1 and E1 IO to MMB and part P. The total primary no-load current of the I/O and the total component of the OM-MIO cannot be added arithmetically. They are not in phase but are added geometrically combined with the parallelogram of the forces. When the transformer is supplying the power, the approximate unit power with the factor of the secondary current is approximately in phase of the secondary voltage of the corresponding load current component with the primary, the opposite with the balance of the secondary amp to determine the maintain automatic transformer of the power of the primary and secondary. The relationships are shown in diagram A with the figure 6. When secondary unit is nearly unit power factor of the non-inducive reluctant load, the total primary current OI 1 is no more near the phase of the primary impressed voltage, no load current OI 0. When the secondary feeding of the high voltage load of the lower power factor of secondary current OI 2, the diagram B for the far beyond with the second voltage of E2 and consequently time total primary current with the OI 1 lags farther behind the primary. Figure 6 shows effects of secondary power primary factor primary current factor. It's kind of OI2 secondary current, OA balancing primary load current, OIO no load primary current, OI1 total primary current composed of load and magnetizing components of OA and OI0 and OE1 is impressed primary voltage. A complete transformer vector diagram is shown in figure 7. This shows the vector diagram with the cosines and tangents and everything shown in the line space. Complete transformer vector diagram. OE2 is included in the electromagnetic force secondary hypothetical. OE1 is inducing an electromagnetic primary portion of the OE2 and the ratio R. R is the ratio of the transformation of the transformer. OI uses a flux. OIO primary no load current. OI1 total resistant primary current. And then I can't read the next one. But constant cosine O2 power factor load of the secondary OE1 total voltage to be applied with the primary terminals. E2 C2 secondary resistance drop in the volts of the phase of the OT. E2 C2 E2 C2 is the secondary resistance drop due to the secondary leakage of the age flux in 90 degrees of OI2. OA is the primary load current with the opposed with the proportional OI and by the ratio 1 and R. OE2 is the next secondary terminal voltage cosine O1 power factor of the primary current. The voltage OE must be larger than the OE1. The high voltage applied with the primary terminals by the amount of necessary to overcome E1C1 or plus E1C1. Secondary terminal voltage O2. Next, the net secondary terminal voltage less than the fully induced secondary voltage OE2. The amount of loss resistance drop by the E2C2. Secondary resistance drop in the phase with OI2. Plus the resistance drop of the E2C2, the secondary resistance drop of the voltage, secondary leakage of age flux in 90 degrees of the OI2. This loss must be subtracted originally, including the voltage of OE2, net secondary terminal voltage, the net terminal voltage of the secondary OE2, net secondary terminal voltage. I guess I didn't have to read that with that. Alright, your types of transformer. The essential part of the transformers are the coils with the insulation, the iron core, the terminal board, the lead-out wires. In the case of any with the insulation, the transformer is used. The single work may either be the dry type self-cooled or oil immersed and self-cooled, depending on the capacity of the transformer. The dry type of the transformers are generally used with primary voltage up to 660 volts. Above 660 volts, and oil immersed transformers are usually used. Formerly, some of the railroads on central fed track circuits, the track transformers adjust the magnetic leak of the blocks in the iron core. These enable to use the resistor and reactor as a limiting device between the track and secondary track to be eliminated. Leakage block produced by the same effect of the reactor in series with the secondary of the transformer. The amount of reactions being made adjustable movement of the block. This type of the transformer is generally superseded by the use of the constant potential transformer external resistor reactor, but limiting device of present use of the reactive transformer, that is a transformer adjustable leak blockage, has been practically limited to the dry type of the reactors charging batteries. Another type of the transformer used in signaling is the auto transformer shown in Figure 8. Figure 8 shows the laminated core V1 and V and V1. The ratio depends on the number of the turns in each part. V is the primary, V1 is the secondary. This transformer's high voltage should be used only where the small variations between the primary and secondary on a low voltage. Any type of the transformer used on a single work of the insulation transformer, which has the same number of the turns primary and secondary winding, usually called one-to-one transformers. These type of these generators, lightning surge ground protection between the transmission lines and operated units where the power is purchased from the outside of the source, supply additional protection between the outside of the source and supply and transmission lines. This is also a series of current transformers shown in Figure 9. The line goes around your primary, secondary series of loaded. Figure 9 shows your series of current transformer. In series of the current transformer, the primary coil is series with a series with only one line wire. Secondary in the series with the apparatus with the transmits the energy with the current of the primary varies. The current secondary is proportionally with the type of the transformer generally operated with the ammeters, watt meters. Such current transformers are usually designed to cable the current with the 5 ampere through the meter with the secondary circuit with the specified full load current in the primary circuit. The ammeter is calibrated in terms of primary full load current. The relative arrangement of the core and coil divided in the transformer is generally used with a single work iron type into core type, shell type, and disturb the core type. There are three types of the type shown in Figure 10. The core type has vertical legs surrounded by the winding, half the primary and half secondary around one over the other of each leg, and then it cuts off. Figure 10 shows the transformer core solutions. This shows the different. This shows the windings and different branches round two cores, or through one, or in cross sectional times, or cores times shell type times distributed type. Shell type of the primary and secondary would be interlaced with one other over the center leg of the iron core, which is almost entirely surrounded by the coils. The Figure 11 showed the shell transformer, the transformer terminal board as shown at the left, and the transformer enclosed in the iron case with the lid off and shown at the right. So on the left, you have your shell transformer. The distributed core transforms the combination of the core shell type. The iron core consists of 4 magnetic circuits equal to the reluctance of the multiple. Each circuit consists of a separate core. One leg of each magnetic is built in 2 different widths of the something in coil at equal distance with the center of the 4 sides. The complete core of the coils of the Figure 12. Figure 12 shows the distributed core transformer. A relative advantage of the core shell type. The core type has a lighter core with a smaller sectional area with the shell type. The more the copper, larger the number of the turns required with the core type. Although the turns are less means the length, again with the cylindrical from the wounds, coils may be rapidly warmed from the core type. Though these coils have large surfaces exposed with the coiling, the core type is better suited with the high voltage, which may require the many turns of considerable insulation. Shell type is suited with the moderate voltage, requiring few turns of little insulation. Distributed core and type of the combines with the best feature of the both core and shell. The type of the i.e. short the means of length of the turns in coil, the short length of the magnetic circuit. Modern type of the transformers. Recent improvement in design with the technique manufactured results with the reduction size of the weight of the transformer of the distribution type. The developments have produced the core in which the magnetic flux is parallel to the direction of the roll and parts of the core, which enable the marked reduction in the core's loss to be obtained. The new core of the structure is obtained with the four ways: the assembling core with the strip of steel sheared in the direction of the rolling by the winding of the continuous stripe of the steel through the opening of the performed coil, by winding cores the steel strips of steel within winding the coils around the core, meaning the motor-driven collapsible coil from the forming of fixture, and by winding cores of the formed continuous strip steel, then the producing of high voltage at low voltage because of the breakdown of the insulation, such that the failure could be hazardous to the person handling the signal apparatus might cause the damage to the apparatus. Interlacing the windings makes it more difficult to provide adequate insulation between the primary and secondary. Alright, cotton covered wire is commonly used with the winding when this has become saturated and impregnated compound. The varnish is to provide with a good insulation between the adjacent turns of the winding. Additional insulation, such as layers of insulation paper or cloth, is required between the primary and secondary windings, sometimes used with layers, especially high voltage winding with a large number of turns. After the core is completely wound, they're thoroughly dried, and heating of the vacuum tank of the adds often, which the high insulating compound is forced by the high pressure in every part of the winding of the until they're thoroughly saturated. The varnishing meet the substitute of the insulating compound applied with the winding under the pressure, and the small transformers winding is dipped in the varnish. The process is making the windings moisture proof. Dielectrical requirements. Transformers or railway signal surfaces are required to withstand the following of the 60 cycles or RMS, or dry type self-cooled transformers. Assembled transformers shall withstand 1 minute of a 60 cycle installation testing. Place of manufacture 3,000 volts between each of the winding. Other metallic parts will insulated therefrom, except where specified otherwise. Transformers winding the rated with more than 175 volts withstand with a 1 minute of 60 cycle installation testing. Place manufacture of 10,000 volts between the such and winding and other metallic parts insulated there, but from except with the winding rated with more than 175 volts, less than 255 volts, mode designated with the connected with the local line, and the load would be tested with West and 3,000 volts. With the secondary associated adjusting secondary, the insulation between the shall withstand 1 minute of 60-second installation bolts placed at a manufacturer of 500 volts. D. The surface leakage is insufficient to withstand the dielectrical testing in the paragraphs 1 and B shall be provided between the exposed metallic part and the apparatus carrying current with any other metallic part thereof. Surface leakage distance should not be less than 1/3 of an inch. A potential of twice the normal operating requirements at suitable frequency shall be impressed across the windings for 1 minute without any excessive flow of current indicating the short circuit. 2. Oil immersed self-cooled transformers. A. The transformer winding should be insulated to meet unusual blank. I don't know. The standards marking on the external leads with accordance with the AIEE and ASA standards indicating the polarity external leads of the transformer illustrated with figure 13 with the symbols H1 and H2 for the high voltage leads and X1 and X2 for the low voltage leads. The H1 and X1 indicate the leads with the positive polarity. H2 and X2 the leads with the negative polarity. Figure 13 diagrammic plans viewing load locking down the transformer shown in the simplified manner in which the transformers are wound with the relative position managing the bringing out of the high voltage leads. Are arrows indicating the relatively direction of the current flow in the windings within plus or minus signs shown merely to indicate the polarity. The ends of the coil are not to be used in primary polarity marking for the external leads. High voltage, low voltage, X1, X2, X1, H1, X2, VH5, V11, high voltage by low voltage. This figure is the polarity of a single phase line transformer. Adapted to polarity is illustrated. Assuming the instantaneous direction of the current flow is the lead H1 is in as shown by the arrow to plus sign, it seems that the same instant with the current flow of the low voltage at lead X2 is shown on the arrow minus sign is also in inches. The train holds this holds the true because of the direction of the instantaneous current flow of the two parallel lines, high voltage, low voltage windings, in the same side of the core must be opposite of the side of the current flow for the source of the feed for the high voltage winding of the instantaneous positive, instantaneous negative, the lead H for the current flow for the positive, lead H2 for the current flows for the other out negative at the current flow for the low voltage and winding. The external circuit is also instantaneous positive, instantaneous negative is shown as evident in lead in X1 and is positive and X2 is negative. Calling the voltage between the leads and high voltage is winding VH for the voltage between the leads of the low voltage winding VL is also seen when voltage VH is impressed with the high voltage winding of the lead H1 and X2 connected together. The voltage VH plus the VL the voltage high plus the voltage low indicated by the voltmeter connected with the leads H2 and HX1 arrangement of the leads said to be have additive polar if the ends of the low voltage polarity would be subtractive. The method tests aim its polarity by alternating voltage test. The generator practices inductive polarity winding with the dry type of the air-cooled transsignal transformer that be binding with the post of the terminal board without leads. Therefore, it is either designated with the positive post of each of the winding plus a sign with no designation for the minus sign, or to show that the plus sign is the positive post with the minus sign of the negative post of each winding. Assembly. Practically all transformers have terminal boards attached with the core, which is attached with the primary and secondary coil leads where the primary voltage is very high, but the primary leads are not bought into the terminal board. The transformer is put into the case and firmly attached to the case to keep it steady during the transient. The transformer outdoor surface is provided with the leads and insulated copper wire terminal bushing sealed in the case. Oil immersed sealed transformers. Transformers having windings rated greater higher than 660 volts and the size of larger than 2 kilovolt amperes. The large volts is usually assembled the liquid height in cast iron sheet metal is cast and the permanent core of the windings to be immersed in fine grade mineral oil free of the acid, alkalines, or moisture. The case provides mechanical weather protection for the core and windings of the oil, keeps the moisture out of the windings, provides the insulation and medium of the rapid transfer heat of the core windings of the metal case that is dissipated with the thence and surrounding the atmosphere, oil being much better than medium of the air and the heat transfer. A dry type of self-cooled transformer would have the considerably larger of the oil immersed self-cooled transformer, the same kilovolts at amp the rating with the order to maintain the same temperature rise at the core of the windings. Figure 14 and 15, the oil immersed self-cooled transformer. Figure 15, a high tension line transformer. Dry type self-cooled transformer to transformer primary voltage 660 volts or less, capacity of 2 kilovolt amperes. Less generally the dry type self-cooled. The windings are. This is figure 10, the dry type self-cooled transformer with the cross arm mounting. They are. The cast iron bells are to protect with the winding of the core and the coil assembly is enclosed with the moisture-type shield case, usually arranged with the cross arm mounting with the B bolted against the wall. External lead the double-braided insulated wire are brought out of the lower end of the bell bottom of the case through the insulating bushing. The transformer, when used with the crossing and mounting, is generally connected directly to the single transmission lines are known as line transformers. Figure 16, indoor mounting, particularly a small rating of the core coil, and something commonly includes with the shield steel K, which may have ventilating holes, terminal body insulated material such as model bakelite on the top of the front of the case is illustrated in Figure 17. Figure 17 shows a dry type track and single lighting transformers with indoor services. Your dry type transformer for the indoor services generally used for the track of the signal lighting purpose. The transformer may be built with 25 to 60 to 100 cycle. The figure 17 shows the transformer type, the capacity of these transformers, single, secondary, primary voltages over 115 volts or less, are as follows: capacity in volts or amps. Size WF W5 is 25 cycles at 75 volt amperes, 150 volt at 60 for 60, and 200 amperes for 100 cycle. The size W10 has 150 volts at 25 cycles, 300 volts at 60 cycles, and 400 cycles. 400 at 100 cycles. 420 has 300 cycles at 25, 600 volt amperes at 60 cycles, and 800 volt amperes at 100 cycles. If more than one secondary is used, and if the primary is insulated with the higher voltage, the above capacity will be somewhat reduced. The secondary will be one of the usual voltage required with the track signal lighting rectifier provided with the taps and voltage adjustment, primarily used with wound at 57.5 volts and even multiple thereof. For 250 volt higher primary voltage insulated with primary leadings are brought out with the case of the insulating member. The reactive transformer. The reactive transformer is one of which for the adjusting magnetic leakage block laminated iron provided with the diverted and appreciable part of the magnetic flux operating with the primary secondary portion of the core with the amount of flux diverted but can be varied and adjusted by the leakage block. Ultimately, the effect of the same would be obtained by the using adjustable reactor in series between the secondary and load. Figure 18 shows one of the form of the reactive transformer, which is used as the component part of the dry plate battery charging rectifier. The transformer supplies the proper voltage rectifier cell assembly required for the reactive's ballast adjustment and charging rate. Figure 18 shows the reactive transformer used for the dry plate type rectifier. All right, your light transformers. Transformers connected directly with the transmission line collected, called the line transformer. The generally dry type of the line voltage is 660 volts or less. Oil emerged with line voltage over 600 volts. Formerly, oil emerged line transformers were sometimes furnished with the two secondary, one of the 110 volts, the second with the track voltage. However, the practice is, and this shows a figure 19, assemble cool cores and oil cooled line transformer. So you have your winding, your wraps, and your terminals. Um, this is kind of like the figure 20. It doesn't say, but this is a transformer, kind of like the ones you find your on top of your street lamp. Figure 24 is an ELF transformer. Certain sizes in inches, A, B, C, D, and E, F, G, H. These are all the dimensions. There's 6 different sizes, and that concludes um, American Railway Signal Principle in Practice, Chapter 8, Transformers.